Hello, my name is Marco Riani.
And my name is a.c.atkinson. This is a further video about our forthcoming book on robust statistics, written by the two of us together with our co-authors Aldo Corbellini, Domenico Perrotta, and Valentin Todorov. The purpose of this video is to provide a simple, straightforward example of the use of the Johansson transformation, that is, an extension of the Box-Cox transformation to responses which may be either positive or negative. The data are experimental results from a university class at the University of Queensland. In our book, these data are called the heart rate data. They give the pulse rate of students before and after exercise. The web page reference is given in our book. Here is what you find when you get to the description of the data. Students in an introductory statistics class at the University of Queensland participated in a simple experiment. They took their own pulse rate. They were then randomized to run in place for 1 minute or to sit for that minute. Then everyone measured their pulse rate again. There are 109 complete observations, 9 explanatory variables covering physiological and lifestyle data, and the 2 pulse rates. We analyze these data by taking the difference in the 2 pulse rates so the response can be either positive or negative. The analysis of these data is set as a problem 10.1 in the book, and there are a list of questions to be answered. Here, we do not follow that analysis precisely, but try to give a coherent account of what we see as the important features of the data analysis.
We load the data and we prepare our Y and X metrics, and we start with a automatic variable selection procedure. The variable selection procedure suggests that just variable x9 is significant, and it has a p-value which is very small. The R square is a bit smaller than 0.8.
The interpretation of this is somewhat surprising. x9 is whether the students sat or ran for 1 minute, but you would expect perhaps that some of the other variables, like whether they were in training or not, would have had an effect on the difference in pulse rates. However, this seems not to be the case. One might wonder whether if they've been made to run for much longer, 5 minutes, 10 minutes, the fitness of the students would have shown up, but we have no data that would help us to answer this question.
Now we try to check whether the data have to be transformed. So this is a typical Venn plot.
This plot is for data in which all the 9 explanatory variables have been used in the model.
This Venn plot considers the values of lambda from 0.5 square root transformation up to 0.8. The trajectory for 0.7 is always inside the bands. On the other end, the trajectories respectively for lambda is equal to 0.6 and 0.8 go out of the bands. The trajectory for the square root is rejected starting from m around 100. The trajectory for lambda is equal to 1 is not shown here because it is firmly rejected during the search. Therefore, the data have to be transformed. So now we transform the response according to a value of transformation parameter that was suggested by the Venn plot, and we do a variable selection in the transformed scale, and here we find once again that x9 is the only one important variable.
So we now move to consideration of the transformation of the response when we only have x9 as an explanatory variable. The right-hand panel of figure A67 shows the fan plot for deciding whether one parameter is good for both positive and negative observations, or whether there are different parameter values are needed for the positive and negative observations. We thus have three trajectories. One is testing the overall parameter value, one is testing the parameter value for the positive observations,
the green dotted line,
and the other is testing the transformation for the negative observations,
the black dotted line.
If one parameter value is satisfactory for both tails, the trajectories of these dashed lines will be close together and close to the trajectory of the overall transformation parameter. We can see perhaps most clearly that this is true for the square root transformation at the top of the plot, which we are not considering. If we go down just to the bottom of the envelopes, we can look at the trajectory for 0.7. The purple line is the trajectory of the score test for the overall statistic. The fan plot of figure A67 is somewhat crowded, so we now just look at the fan plot when the transformation is 0.7. The blue continuous line is that for the overall value of lambda, transforming both positive and negative observations. The green dashed line, which lies very close to the blue one, is for the transformation of the positive observations, and the black dashed line is for the transformation of the negative observations. The green and the blue are close together. The black is a little further apart, but all of this is happening well within the envelopes, so there is no significant evidence of a need for different transformation for the two kinds of observation.
Now we want to compare through the QQ plots the residuals in the original and in the transformed scale. This is figure 8.68, and there is a big difference between these two residuals. The left panel refers to the original scale, the right panel refers to the transformed scale using lambda equal to 0.7.
The QQ plot for the untransformed data in the left-hand panel shows symmetrical long tails, which are much reduced in the plot in the right-hand panel for the transformed data. Normality has been better approximated by the transformation. In particular, the upper tail of the distribution for the transformed data is now close to normal. A minor feature of both plots is the occurrence of horizontal paths corresponding to the repeated response values in the data.
So we wanted to do the comparisons both in terms of QQ plot and also in terms of box plots. The difference between the left panel untransformed data against X9 and the right panel transformed data against X9 is overwhelming.
In the left-hand panel, the responses for low values of X9 are very close together, whereas when X9 is positive, the results are much more spread out. Students are presumably behaving rather differently to having been running in place, whereas the ones that are sitting, there has been very little change in their responses, so the scatter of the two box plots is very different.
On the other hand, the scatter of the two box plots in the transformed scale is much more comparable. Finally, notice the presence of an outlying observation which has a value of the difference of pulse rate much smaller than that of the other observations. This outlying observation was not evident at all in the original scale.
Of course, what we're really looking for is strong evidence or otherwise for the effect of X9. And you can see that in the box plot of the right-hand panel that those for X9 equal to 1 is similar to that for the lower value, but the location is appreciably increased. This is what the regression analysis is telling us.
It's a curiosity if we repeat the analysis and instead of the box plot we create the violin plots. It is clear now that the shape of the two violins is very different in the original scale. On the other hand, is much more similar in the transformed scale. Notice this is due to the outlying observation. Now we want to do outlier detection in the original and the transformed space. You can see that the number of outliers detected by the follow search in the original scale is 17. On the other hand, there is no outlier in the transformed scale. If maybe we want to see the position of the outliers in the original scale, you can see that the outliers correspond to a particular range of values of y. This is an indication indeed that there is something wrong.
There is something systematically wrong in the model that has been fitted to the data. One of the interests of our book has been to compare methods of robust regression. For example, we spent a long time determining whether the form of the row function matters very much. Here we look at MM estimation using the Tukey byweight row function.
And then we plot the residuals in the case of original response and then in the case of transformed response. The confidence level that we use is a simultaneous confidence level, and these are the results. While in the original space you find a lot of outliers, in the transformed space there is just one unit which has been declared as outlier, which is marginally outlying in the transformed space.
This is also the unit which showed itself dropping down at the bottom of the left-hand violin plot in the transformed data.
Well, in fact, if we go back to figure 8.69 and then if we click on this particular point, we see that it is referred to observation 40. For this is the observation which is just outside the lower confidence band. Let us come to the conclusions for this example.
In this example, we have seen a straightforward use of the Yeo-Johnson transformation, which has greatly improved the approximate normality of the data and led to a much more powerful data analysis. We have also shown that in this case, unlike some of the other examples in the book, it is not necessary to extend the Yeo-Johnson transformation and to have different parameter values for positive and negative observations. Finally, we have shown that the identification of outliers in this case does not depend strongly on which robust method is used, but that a robust method must be used, or there are outliers, if not everywhere, appreciably so.
So one may think that a value of lambda equal to 0.7 plays a minor role. On the other hand, here we have seen that there is a significant difference between the analysis using lambda is equal to 1, no transformation, or lambda is equal to 0.7. And then we also saw that was the need of a fine grid of values of lambda. In fact, as the sample size increases, as we have seen in several examples of this book, you need to have a finer grid of values of lambda. Thank you for watching and see you to the next videos. Please leave us your comments.
Yes, thank you very much. We hope to be speaking to you again soon. Bye.
Bye.